Basically, on your formula sheet, we're just going to start ticking off all those different other remaining formulas for hypothesis tests and confidence intervals. I put this same flowchart up again on how we understand whether to use a t-distribution or a z-distribution. We've kind of come to two of the three branches. We've done confidence intervals and hypothesis testing for one sample proportions using z-scores. We've done confidence intervals and hypothesis testing for means with known parameters, also using z-scores. Standard 22 talks about to start using a t-test, a t-score, to do a hypothesis test for means with unknown variances, means with unknown parameters. Doing inference with means, you have either one of two categories. You either have a known parameter or an unknown parameter. You're either given the overall population standard deviation, or you take a sample, and the best you can do to estimate the variability is to record the standard deviation of that sample. Because we're estimating the overall variability, my data has more error, and I need a more conservative distribution. Conduct my inference, so we use a t-distribution as opposed to the z-distribution. Unknown parameters are also usually associated with small sample sizes. Sample sizes of less than 30, because after about 30, remember that graph on Desmos I've showed you before, for sample sizes of about 30 or higher, is there any real difference between the t-distribution and the z-distribution? No, they're approximately the same, right? So typically, unknown parameters and a sample size of less than 30 kind of go hand in hand. We'll use a t-distribution to conduct a hypothesis test for what sample means. Over on the right side of that, there's a couple of different things to highlight before we get into the first hypothesis test. The test statistic for a one-sample t-test of means with unknown parameters is t equals x bar minus mu. X bar is notation for what? Sample mean. Mu is notation for population mean. So when I take a sample and record the average of that sample, I'd expect the sample mean to be the same as the population mean, because I'm just sampling from that population. I'd expect that my sample mean to be the same. But sampling is random. I might get more than I would have thought for the average, or less than I would have thought for the average. Take that difference between the two means and divide by the standard deviation of the sample mean, S over root n. We're estimating the overall standard deviation using this sample statistics, using the sample standard deviation S, as opposed to using sigma, the actual population standard deviation. That's why I'm using a t-score as opposed to a z-score. The conditions for inference for small sample sizes, unknown parameters, are very similar to what you've seen before. I have to have a random sample so that it's not biased. Take a random sample to collect your data. My sample size needs to be less than 10% of the overall population. I want each sample to be independent, so I can't take too large a slice of the population. My sample size generally needs to be less than 10% of the overall population. And like I said, my sample size needs to be less than 30. Sampling can be an expensive and time-consuming process. Sometimes, in many cases, it's not very feasible to take a large sample of over than 30 and be able to use a z-score. That's why the t-distribution came about. If we're only able to collect a small sample size, we need a more conservative distribution, and we'll use t-distribution as opposed to z. On your formula sheet, you have that same test statistic, x bar minus mu divided by s over root n. If I flip to the back side, we used a couple of these before. Back in standard 21, we did some basic z-tests. We used a one proportion z-test. I took a sample, recorded the proportion from my sample, and compared it back to some previous benchmark or hypothesized value. That's a one sample proportion hypothesis test. We also did the same thing for a means with known parameters hypothesis test. I took a sample, recorded the sample mean x bar, and compared it back to my hypothesized or benchmark I'm trying to compare it back to. One sample z-test for means with known parameters. The one just down below, I'm going to use for the rest of this week. A t-test formula for means with unknown parameters. Use a t-score given by x bar minus mu, or s divided by the square of sample size n. Remember, the t-distribution has a degree of freedom given by n minus 1, the sample size minus 1. One sample tests are good for when you want to compare it back to a benchmark. I take a sample, I want to record the sample statistics compared to some hypothesized or benchmark value to see if I have changed the population in some manner. All right, so let's try this. Yeah. Oh. Let's use those conditions and test statistics to conduct this one sample means hypothesis test using a t-score. The call center at Wells Fargo Home Mortgage advertises a wait time of no more than 5 minutes for its customers calling in to request their services. Public Relations Department at Wells Fargo wants to be sure that this claim is true and conducts a customer survey at the end of every call to the help center. Results of the survey are shown below. Is this enough statistical evidence to support a customer wait time of less than 5 minutes? For those that call into Wells Fargo. You ever called into some help center and at the end of the call you have to take a customer survey about how they did on the call? Well, you will. Usually when you call Mediacom or Wells Fargo and you talk to the help center to try and get some assistance, at the end of the call they say, hey, hang on for a quick short survey to see how the customer responded to the help that they did. Wells Fargo is trying to see if the wait time was no more than 5 minutes. You call in, you have to wait a little bit to talk to somebody. Hopefully that wait time isn't more than 5 minutes, or you might get kind of angry about it. So the PR department took a short sample of customers and recorded their wait times below. Is this enough statistical evidence to see if the wait time is no more than 5 minutes? So we have the actual sample data here. On your Google Sheet, on your laptop, let's get this typed in and record the sample statistics. I'm not given the data. I want to know what the average of the sample was, what the average wait time was, and what the standard deviation in that wait time was. What is X bar and S? Sometimes for doing hypothesis tests, rather than give us the data, we actually have to record our own statistics, calculate the data ourselves. Should be 15 different values. There's 5 rows of 3. As you guys did on your quiz yesterday, equals average. Then I'll highlight the data set. These 15 customers, their average wait time was 3.933 minutes. With a standard deviation of 2.12 minutes. 2.12 minutes. This is a one sample test. I take a sample of call times and I want to compare it back to some hypothesized or benchmark value. What is the overall expected wait time for calling into this help center? So let's call that. I have an expected average wait time for everybody calling into this help center of 5 minutes. I want to see if any difference between these two values is statistically significant, or is that difference just associated with normal random variability? I just happened to find 15 people whose wait time was a little bit less, and that is not any suggested real difference between these two values. So let's get into the steps of a hypothesis test. In order to use a t-distribution, I have to make sure that my data was collected randomly and independently. I assume if this was a random sample of customers. Sample was collected randomly, so there was no sample bias. Sample random customers. Sample is random. It's 15 different customers, probably less than 10% of all the customers that call into the Wells Fargo hotline. And if we're going to use a t-score as opposed to a z-score, I want to make sure that I have a small sample size, or I have an unknown parameter. My sample size of 15 is certainly less than the convention of 30 in order to use a t-distribution. Step 2 is record your hypotheses down. H sub O, H sub A. What's the null and alternative? Since we're talking about means, we're going to frame them in terms of mu, population mean, our parameter. How will we set up our hypotheses in order to test this down? To see if their claim of waiting no more than 5 minutes is valid. For which one? The null H naught or the alternative H sub A? Oh. Let's assume that they're hitting their target of 5 minutes. No more than 5 minutes. What would their alternative be? I want to see if the claim is valid. So let's assume that they're not going to do it. See if we can collect data to prove that they are less than 5 minutes. Step 3, if I remember right from those steps about hypothesis test, is to record the rejection region. Let's use a graphical approach to see if we can either reject or fail to reject an hypothesis. Are you going to look up the critical score on a Z table or a T table? T or Z? T. All right, so grab your T table. Since we have means with unknown parameters, what does the unknown parameters refer to? Unknown parameters. What does that refer to? Am I using the population standard deviation to estimate the variability or the sample standard deviation to estimate the variability? Sample. The best I can do is take a sample of 15 values, record the standard deviation of the sample as a way to estimate the overall variability in the population. By looking at some and not all, might I have made an error? Might there be some error and difference between the overall variability versus the sample variability I'm trying to estimate? By only taking the sample standard deviation, could I maybe be off a little bit in terms of estimating the overall variability? Yeah, so I need to use a t-distribution as a more conservative estimate. That's why we're looking up a t-score for our rejection region as opposed to a z-score. All right, so my t-table is here. Do we have either a 1 or 2-tailed t-test? How do you know 1? How do we know we're using a 1-tailed test? Less than. Don't say less than. Isn't this the left tail? So we're going to be a 1-tailed test at the 5% significant level to be within this second column from the left. With how many degrees? I know I'm in this second column from the left, but which row do I have to? 14. So 1.761. However, if it's the left tail, wouldn't it be negative 1.761? Draw a sample t-curve with those nice fat tails on either end. I want to find the t-score that cuts off 5th percentile from the remaining 95% of the distribution. Negative 1.761. I can calculate a t-score based off of my test statistic here and sample data here. I'll be able to reject the null hypothesis. I can calculate a test statistic that is more extreme, further from 0 than negative 1.761, I have significant results. If not, we have to fail to reject. Test statistic would be t equals x bar minus mu divided by s over the square root of n. I guess I didn't write n down before. How many data points were in the sample? 15, which is why I had 14 degrees of freedom. Plug everything and go into the formula here. T equals our sample mean of 3.933 minutes minus our hypothesized wait time of 5 minutes. Take that difference from what we'd expect of a wait time, making a call into the help center. Take that difference between the two wait times and divide by the sample standard deviation. 2.12 over square root of 15. Could you guys type that in your calculator? Let's see if we get the same t-score to compare back to our rejection rate. .933 minus 5 divided by, what's the standard deviation again? 2.12 minutes over the square root of 15, about negative 1.95949. So using a graphical approach, what should our decision be? Do we either have significant results and reject the null hypothesis, or do we lack significant results and have to fail to reject? Where would this t-score fall within the distribution that you graphed in your rejection region before that? In the tail. Because isn't negative 1.95 further from 0 than our rejection region, a critical score of negative 1.761? Be about here, wouldn't it? It'd be further into the tail than this given value, defining our rejection region, negative 1.761. Another way to make the decision is to record in step 5 what is called the p-value. When we were doing the z-test back in standard 21, you could just use your z-table to look up this p-value. Sorry, Jess. It's a little bit different when we have to use a t-score. We're going to kind of talk about maybe one of two ways to do this. Everyone look at your t-table for a minute. Now let's get an estimate of what our p-value would probably be before we use sheets. On your t-table, I know I had a one-tail hypothesis test with 14 degrees of freedom. I'm going to be using this row to kind of estimate what my p-value might be.
Lily Jacobs, please report to the secondary office. Lily Jacobs, report to the secondary office.
I had a t-score of negative 1.949. Between which two values would that fall? Negative 1.345 and negative 1.761. Would my t-score fall within those two values? Negative 1.34 and negative 1.76. Would my t-score that I calculated fall within those two values? No. No. Would my t-score fall between negative 1.761 and negative 2.145? Remember, I'm using just the negative of all of these, using a left-hand top. Yeah. Because my t-score is between those two values, the p-value for that t-score is between 5% and 2.5%. Because my sample statistic of negative 1.949 is between negative 1.761 and negative 2.145, the p-value for that t-score should be between 5% and 2.5%. All you can get from the t-table is just an estimate of the p-value. To get a more precise result, we have to use Google Sheets. The coding on Google Sheets is equal t-dist. It's going to give us the p-value for a specific t-score given a certain distribution with degree of freedom. So let's go on to Google Sheets, since you all have that opened up from earlier. Let's get that. So equals tdist. And that help menu should tell you what you have to type in. Data. All right, so into some empty cell equals tdist. It's going to calculate the probability of a specific distribution with a given input, our t-score. So first up, it needs our t-score, some x value, some t-score that we're going to type in. Sheets has to use the positive version of this. So even though it's negative 1.949, we're going to type in positive 1.949. Just like all the positive scores on your t-table. And then hit a comma. The next thing is the number of the degrees of freedom so that Google Sheets knows what type of t-distribution we were using. How many degrees of freedom were given for our hypothesis test? 14, hit another comma. The next thing that Google Sheets need is the number of tails. Is this a one-tailed hypothesis test or a two-tailed hypothesis test? If it was two-tailed, it would take this p-value and just double it because it could be extreme in either direction for each of the two tails. We only need one tail, so it's going to leave us with the 0.0358 p-value. Does that sort of make sense with how we looked at the t-table from earlier? Using the t-table, we said that our t-score of negative 1.949 falls within this range of t-values, negative 176 to negative 2.15. If my t-score falls within this interval, should my p-value fall within the same interval between 2.5% and 5% from above? Yeah. My p-value is about 3.6%. Remember from last week, I think about every single day last week when we were doing standard 21 hypothesis tests, I asked you, what's the definition of a p-value? Well, what is that definition? In regards to hypothesis testing, what is a p-value by definition? Probability. P is for probability. Okay, we're getting closer. The probability of something if the null hypothesis is true.
Sample or sample ones.
So the probability of us finding our sample data, or data more extreme, and then what Kellen said if the null is true. Let's put that in context. If it's actually true that the average wait time is 5 minutes, I would find 15 different customers with an average wait time of 3.933 minutes about 3.6% of the time. I want to reject a null hypothesis that's true only 5% of the time. Do I fall within that allotted error? Is 3.6% within the given type 1 error probability of 5%? I want to reject this and have the null hypothesis be true only 5% of the time. Does this p-value fall within that allotted error? Yeah. So what's our decision going to be?
Reject.
Reject. The same decision you made by using the rejection region graphical approach from prior. Reject the whole. Reject H9. Last but not least should be the conclusion. What does this mean in context? About wait times, calling into the hotline. Our evidence says what?
evidence says that there'll be a less wait time of 5 minutes.
Our evidence suggests that this claim is probably valid, right? I would expect a wait time of no more than 5 minutes, less than 5 minutes, for customers calling into the home mortgage service line. Evidence suggests that customers are waiting less than 5 minutes calling into Wells Fargo. Next week, you're going to have a quiz on type 1 and 2 errors to reassess that standard. So if I made a mistake, what type of error did I make? A type 1 error or a type 2 error? Review that maybe for a minute. That's going to come up here sooner rather than later. If I made a mistake, what type of error was made? Was it type 1 or 2? Second? 1, type 1. I agree. Why? I reject the null hypothesis because I think it's false.
Positive.
What if I reject the null hypothesis when it's actually true still? That's a type 1 error that I made. If I made a mistake in rejecting the null hypothesis, I reject the null hypothesis when it's actually true. But what's the probability of that actually being correct? What's the probability of my null hypothesis being true if I found my sample data? 3.6%. What's my type 1 error probability that I was given? 5%. So I'm going to reject the null hypothesis because I'm within that allotted error that I was given to start the hypothesis. I want to reject a true null hypothesis no more than 5% of the time. This is within that value, so we had to reject. We have statistically significant evidence. Type 1 error is a false positive. That was somebody said over there. Rejecting the true null. A type 2 error is a false negative. Failing to reject a false null hypothesis. False negative.